Are you seeing my screen all right?
Yeah.
Yeah?
Yep.
Okay. Well, thanks Marcel for giving me the opportunity to talk about my work in this international global fashion. And thank you for your kind words about being a Renaissance man and so on. You see in this picture a dairy pasture. And this dairy pasture is actually not very far from where I'm sitting right now. It's less than a mile away. And there's also some weeds in that pasture. And those weeds, which button do I use now? Oh. Yeah. Those weeds that you see are called broadleaf dock. And it is a weed that you find in temperate grasslands all over the world. When it grows, it replaces the grass, it pushes the grass away, but it produces less dry matter and less nutritious value, less nutritional value than grass does. So if you have enough of it, your cows don't have enough to eat and your milk production will go down. So conventional farmers typically spray when it gets too bad. They use an herbicide, and they have to do that perhaps once a year or once every 2 years, because the weed, this particular weed always comes back. It's persistent because it has a taproot. A taproot that sits below the soil has a large supply of nutrients and carbohydrates, and so even if you take away all the leaves, it will still come back. But conventional dairy farmers manage thanks to chemicals. Organic dairy farmers, however, don't like to use herbicides, and they have no other way to control this weed than basically go out by hand and use a little spade to dig it out and carry it away. That's unpleasant work. It takes a lot of time, and they don't have the time for that. So it's not surprising that in surveys, more than 50% of the farmers, organic farmers, indicate that docks are a problem. And so we built a robot. The robot is in the middle here, with a bunch of farmers around it and myself right in the middle there. And I'm going to tell you a little bit about that robot today. In the first part of my talk, I'll tell you about the weed detection, how it finds the weeds, how it controls the weeds, and how it gets to the weeds, how it navigates towards the weeds. And the second part of my talk, I'll branch out a little bit and say how this project on controlling broadleaf dock in dairy pastures actually gave rise to another project where we are tackling broadleaf weeds in soccer fields. Broadleaf dock is green, and the grass is green also at the time when we want to control the weeds. So we can't use color or any color features to detect the weed. But if you think about it, there is a big difference between grass and weeds, broadleaf weeds, because grass grass has many narrow, long leaves, and a broadleaf weed has broad leaves. So texture provides a characteristic by which we can make a distinction between the wheat and the grass. And so we have in front of our robot a camera that looks straight down. It takes an image of about 1.5 by 1.20 meters. As shown, that's picture A. And then if you zoom in on that and take a look at the place where there's both a piece of wheat and there's a piece of grass, you can see the difference. Where the wheat is, the texture is very even, the gray levels don't vary very much. And the grass, of course, there is a lot of texture. There's a large difference between the bright and the darker pixels. So if you take you divide the big image up in tiles of about 1 centimeter, for example, or smaller or larger. You can quantify the texture of each tile using a Fourier transform. And so if you then plot the spectral power of a tile versus the frequency, the spatial frequency. And you do that, I'm showing that here for 3 tiles in which there was only grass, and for 3 tiles in which there was only dock leaves or parts of dock leaves. And you can see that, that you can, on average, make the distinction. Some grass tiles are just as variable, have just the same spectral power as some dock tiles, but on average, the grass has a lot more power in it. And so, on that basis, we can make a distinction between a grass tile and a dock tile. Now, it's noteworthy that we didn't find a specific frequency, a specific spatial frequency, or a band of frequencies at which grass has at which the distinction between grass and docks can be made best. It seems from this picture that over the whole range of spatial frequencies, the distinction can be made. And so when we use that in image processing, the first thing that you decide, of course, is the size of the tiles. In the top row, the tiles are 0.5 millimeter. In the bottom row, the pixels are 0.5 millimeter, and the tiles are 8 by 8 pixels. In the second row, the pixels are 1 millimeter on the ground, and in the bottom row, they are 2 millimeters. And the gray value corresponds to the spectral power of each tile. So then if you go to the right, we apply the threshold, so we make a binary image, and then in the next step we take away the speckles by removing small blobs, and then in the final column we have applied the dilation and the erosion step in order to bring the blobs that are close together to melt them together. And you can see that we don't need a very high resolution. The 2 millimeter pixels give a very good method of finding the location and the presence of those weeds. This research was described actually in a paper that was published a while ago, and there's some new work coming out soon by a student in our department. That new work actually looks at other measures of texture, more complicated ones that are somewhat more powerful, but do take a lot more computing power also. So here's another slide, basically like the previous one, except these are now images that are collected by our robot while it is actually driving in the field. The top row, you see on the top left color picture, again with 1.5 meters by 1.20 meters. Then the image with the spectral power, then the image with the thresholding applied, the speckles removed, and then finally the image where there's a big blob that indicates the presence and the location of a weed, where the crosshairs are the centroid of that blob, and that is where we will focus the weed control method on. So that's for the top row. The second row is half a second later. Robot has progressed a little bit closer towards the weed, and so on through the bottom image, where the robot has come to a stop, and the weed is now within reach of the control implement that we use. So if you have any questions, by the way, if they're informative questions and they help you to clear up something that wasn't clear, ask them. If you've got questions that are more going into a discussion, then it'd be better to save them to the end, I think. So we put our robot in the field and put it in front of a bunch of weeds that we had selected and let it drive towards it, and then just before it was going to chop the wheat into pieces, we stopped it and measured how far was the place where the robot was going to exert the control, how far was that away from the place where if we had chosen a place, would have chosen to exert the control. And then we see that here that in 50%, this is a cumulative probability plot, So you see that in 50% of the cases, the robot was within 10 centimeters of what we would have chosen ourselves, and that the largest error was somewhere in the area of 20 centimeters. Now 10 centimeters is a perfectly fine, acceptable positioning error, so to speak. But 20 centimeters, if in that case, it would mean that the robot probably doesn't control the weed completely. Now there's also a plot here for that is labeled lab. Those are images that we've taken in a separate pass, and where we had determined, based on the image, where we want to put the control, and where we use the only the image analysis method to determine where the control will be. And so the difference between those two. So that was just in the lab. It didn't involve the physical robot. So the line, the filled circles, that involves both errors in the positioning by the robot, that it doesn't stop exactly at the moment where we want it or the place where we want it, and also errors in the image processing. Why does this the wrong way? Okay. So now we have a method to find the weeds. Once we found them, we need to control them, and we used for that a method that has been proposed actually a while ago by somebody else, and it consists of a cutter, a rotary cutter, which is basically two sharp blades attached to a rod, a vertical rod, which is pushed through the soil while it is turning at about 1,000 RPM. It goes down to about 20 centimeters deep, and remember the taproot of this weed, of broadleaf dock. The aim of this cutter is that the taproot get chopped in small pieces that are small enough that they won't grow back. So you see a cylindrical cover also that is on this cutter. That is not so much to protect people that might be standing close by, but this is a cover that sits on the soil, and when the cutter goes into the soil and loosens up the soil, it works the soil up. It throws the soil up a little bit, and the cover then makes sure that the soil stays in a little pile on top of the, not the hole, but on top of the place where we're doing the cutting or the chopping, and that it doesn't get spread out. And so if it still sits on top of where we've been working, then the next rain shower and together with gravity will help to put that soil right back into place, and so we have a minimal disturbance to the soil. This is some pictures of where we have let the robot control a weed, and then go back a month later, and you can see the condition of the grass after that month. So you might find a bare spot where nothing has grown back on the left-hand side, well, where the weed has been controlled, obviously. You might find a spot like in the middle where the weed is actually growing back. This tiny little green in the middle of the black hole is a weed growing back from a piece of the chopped wood. Or you might find, like on the right-hand side, that the grass and the other plants growing around it have actually covered up the hole again, or the disturbed soil, and there's not a whole lot of chance that the Rumex will grow back in that position. So if you do that, the numbers on that, we destroyed 100 plants on a peat soil in Wilnis and 100 plants on a clay soil in Harlingen, and then went back after a month. And in about 3/4 of the cases, we found that the weed had been effectively controlled. This is from a while ago, and we talked with our farmer that on whose land we've done most of the experiments, and he also indicates now, this is again a year later or so, that he can clearly see where we've been doing experiments. Wherever the robot has been, there are fewer weeds growing now. So that is another indication that this weed control method doesn't work. Well, and then the third part of the robot is how does it get where it needs to be. That is very simple. We simply use a map of the field. We use GPS, and we tell it to go in a zigzag pattern through the field. and we haven't really spent a whole lot of time on making that complicated or very precise even. We just say we start at the point X, you go in a certain direction for a certain length. After that, when you reach that point, you make a half turn and go back, and then another half turn, and so on. And then we use a simple PID controller to minimize the deviation from the path. And so on the straight legs, that is the perpendicular distance to from where you are to where you want to be, and on the semicircular leg, it is the line that goes to the radius of the circle, and it's the distance to the circle. Oh. Well, and that makes a lot of noise, as you can hear. The machine has a pretty heavy diesel engine in there, but you can see how it maneuvers through the field here. It does have a pretty heavy diesel engine because we did this work in close collaboration with a group of farmers, and they were very worried that they might not have enough power. So they said, let's use a nice heavy diesel engine so that we're sure we have enough power. And well, it does have enough power. So the results of this part of the work are, I think, that we have a robot that works actually quite well, at least in some situations. The grass does have to be sort of short and even. The thing is that if the grass is long and you drive over it, or the wind pushes it, or the rain pushes it down, then you can have the situation that lots of grass leaves are start to stick together. And then they start to look a little bit like a broad-leaved wheat, and then of course the image processing is thrown off. Now this is not really a shortcoming, because if the grass is indeed long enough to start to fall over and to stick together, then you certainly don't want to drive through it and mess it up, and you want to go in and cut it. It works also best if the Rumex plants are growing in rosette form, that is that all the leaves are sort of together, and you can more or less recognize separate plants. The thing here is that if your field is neglected enough, you might have that there are very many Rumex plants growing together, and growing into one big mass of plants, basically. And then, of course, your blow detection algorithm doesn't work anymore, because all you have is one big weed, and then also the robot doesn't know where it should be. Now again, this is not a serious practical problem, because by the time you have neglected your field that much, you probably should clean it up in another way, like spraying or so. This robot is really more tuned towards maintaining a more or less okay field. And another thing is that we didn't really take into account enough is we use ambient light. That works very well on days like in the Netherlands that are sort of overcast and things don't change too much. But if you have a day where there's clouds racing across the sky and you have very abrupt transitions from fully sunlit to completely overcast, then a robot may not be so happy. But then the algorithm doesn't work so well either. So again, this is not a serious thing. The commercial version. Maybe somebody can mute their microphones. If you're not talking, maybe you can mute your microphone, because I hear a lot of noise.
Yes, everybody, please make sure to mute your microphone on either the phone or the computer, please. Thank you.
Again, this is not, the light conditions is also not too much of a serious problem, because clearly a commercial version of the robot can take care of this by building a cover and putting lights in the robot. And this work was published recently in the Journal of Field Robotics. I would like then to move on to the second part of my talk, where we used the image processing that was developed for the Rumex robot and applied it to detection and control of weeds on soccer fields. And Marcel mentioned that he likes that because his kids are playing soccer and he doesn't want them to be exposed to chemicals. Well, it's not only people that are on the soccer field actually that are exposed to the pesticides that are used on the soccer field, because typically soccer fields and athletics fields in general, of course, are well drained, so that even after a rainstorm, quickly you can play on it again. But that means that if you apply an herbicide, it will also find its way quickly through the drains and then into the groundwater or into the surface water. So it's the whole population that is suffering from the chemicals applied to sports fields. And I also have a daughter who is playing soccer. She's on the left hand here and she's kicking the ball. So typically a chemical is used to control things like dandelions and other broadleaf weeds on soccer fields, and that chemical is then applied to the whole field, leading to bleaching. And that is unnecessary because, especially on soccer fields, the weeds are clustered. They don't appear throughout the whole field. It's usually around the edges and close to the close to the goals. You find more weeds, and then other places you don't find them at all. So there is a scope to greatly reduce the amount of herbicides used if you were to apply it only where there is in fact the weed growing. And so that's of course exactly what we did, and we collaborated with a couple of companies whose logos are on the slide on the bottom here as well. And we put together a smart soccer field sprayer with a camera mounted in front. In fact, it has 4 cameras now that use the same algorithm as in the case of the Rumex robot to detect the presence of weeds, and then it activates a sprayer if it finds the weeds. There are a number of differences in this project relative to the project where we built the Rumex robot. We decided to build an implement, something that is pulled or carried by a quad or a tractor instead of a robot. And the reason for that is that in this case there is already a routine of controlling those weeds, and that takes place with a tractor and personnel and a certain method of working. And if we come in with a robot and say, well, then that would mean a big change in the routine. Whereas if we come in with an implement that is smart, they can just hook that behind the tractor instead of what they're currently using, and it will not be such a big change in the routine, and therefore we think it will be taken up more easily, more readily. In the case of the dairy farmers, that was different because dairy farmers, the organic dairy farmers, do not do weed control at the moment. So for them, the step to a robot is not bigger than the step to, say, using a particular implement. Another change that we used here is that now we use variance to quantify texture instead of Fourier power. And we should have done that earlier, of course, because I told you that we use total spectral power after using the Fourier analysis. Total spectral power is, of course, exactly the same as variance. We didn't realize that earlier, but now we do, and it calculates a lot faster. Another difference is that on the soccer field, the grass and the weeds are both a lot smaller than in a dairy pasture. There's a finer textured grass, and the weeds are smaller also. So we need a higher resolution, and a higher resolution means more processing time, more computing power needed. And also these tractors are driven at fairly high speeds. 10 kilometers an hour is perhaps the top speed, but it is possible. And that means we need a short shutter time. And it also means that we need to process these images at a high frame rate. And the short shutter time also means that we need to have a light source. We cannot rely on ambient light because then we will not make our, I think it's 20 milliseconds or so, 20 microseconds shutter time. So we used an infrared light source, and the reason we use that was a number of reasons. One of them is that people cannot see that, so if you won't have problems with psychedelic effects, if you see 25 hertz flashing light somewhere. And the other reason is that vegetation, of course, reflects infrared light very well, so you don't need as much energy to get an image. Well, and with the high resolution, the short shutter time, the high frame rate and all that meant that we had to move to a DSP, so we're not using an ordinary computer anymore, we're using a dedicated digital signal processing hardware. And another thing is that we found that it's not always possible to have the same level of brightness in our images. And the reason for that is, among other things, that grass can have very low density, like in this picture, in the spring, say, or after the winter, when there's not very many leaves. But also, it can have very high density with very many leaves on top of each other, and then the reflectivity will be very high, and you get a bright image. So we needed, and we found that our camera was not able to completely neutralize that effect. So we needed an image processing algorithm that was able to take care of these changes in brightness in the overall image that were inevitable. And we did that with a sort of a histogram based method, where we take the peak of the histogram and put it in the middle of the brightness range, the 128 value, and then make the edges of the histogram linear. So a linear rate between 0 and 128 and 128 and 255. And when we apply the algorithm to those 6 images in the previous plot, then you get these images. You see with the higher brightness images that does get a little bit washed out, but the texture is still there where it needs to be. So this is then the kind of result that we get from that. On the top row, 1 image, and on the of the wheat, and then 3 brightness values. Well, the image processing result for if the original image has 3 brightness values. You see that they're more or less the same, and the same thing for an image with no wheats, and again with 3 brightness values. And so we are able to, and here's some Dutch left over in my slide, that we get about 80% correct decisions about the presence of the weeds. So to be precise, 78% correct, 15% false negative, and 7% false positives. And we talked about field managers with these numbers, with field managers about these numbers. And they said, well, if you can tackle 80% of the weeds, we're very happy. Because we do this once or twice a year, we do it every year, and this will keep it under control. And it would mean, of course, that you use an awful lot of less herbicide. This is a picture of the sprayer machine. It's currently not mounted on a quarter tractor. It has its own set of wheels and a handlebar where you can pull it. Yeah, it's got a simple backpack sprayer which we've attached there, which provides the fluid and the pump. And then in the aluminum box there's 4 cameras from left to right, and the computer hardware is in there as well. And the back, you cannot see that in this picture, there are 4 nozzles for each camera. The camera looks at a 25 centimeter width image. So it's each camera has its own nozzle. 25 centimeters times 4 is a meter working with. This machine was just recently completed. We're going to do some tests with it this summer and then later in this year. We expect that will reduce the amount of herbicide by 50%. But I put a 50% number on these slides because lots of people might look at them. But in reality, if there's weeds only growing on 10 or 20% of the field, and you do an 80% detection rate, you should be able to get something like 80% reduction in herbicide use without really giving on the quality of your weed control. So I think this might be a very successful machine, and it is at field scale and practical scale and basically ready to be sold. So by far I have not used half an hour, I think, but I'm going to conclude this anyway. If you want to read up on the Rumex robot, there is a website with movies and pictures and so on. If you want to read up on the smart sprayer, there's a Dutch website with only text in Dutch, because we're focusing this on the Netherlands really. And I've given my email address as well. So thank you for your attention, and be happy to answer any questions you may have.